Thank you very much. Let's see what I have here. So as you were told, I'm going to talk about, ooh, a lot of bright lights. There are people here. I can see your bright lights. As you were told, I'm going to talk about a new approach to designing safety into systems, especially software-intensive systems. So I'm first going to talk about why we need it, which is that complexity in new systems is reaching such a level, a tipping point, where the old approaches are becoming less effective. In addition, there are many new causes of accidents. The result is that we need a paradigm change. We need to change the way we build these systems and change our focus from component reliability to systems thinking. Then I'm going to introduce a new model of causality, accident causality, based on systems theory. It's called STAMP, and then I'll talk about some more new powerful tools that have been created based on STAMP, tools to do hazard analysis, to do accident and incident causal analysis. This is brand new, but in the last couple months, we've discovered that this works for cybersecurity and for security in general. And it's been tried on real systems and is doing better than the old standard techniques for security. So I'll say a little bit about that and some other things. And then I want to talk about, does it work? Is there evidence that it actually works better? Too often, especially in software engineering, we just make sales pitches, but we don't have evidence, real evidence that our techniques work. But in this case, we have real evidence. So first, why do we need a new approach to safety? The problem is that the traditional engineering approaches that were developed for relatively simple electromechanical systems. In fact, all of them are at least 40 or 50 years old, before we had much software or computers in systems. And what's happening in our new systems is the accidents are actually changing their causes. The reasons that the accidents occur are changing. In addition, the role of humans in our systems is changing, and the role of humans in accidents is changing. So we need better ways of dealing with safety in the modern systems, high-tech systems that we're now building. The starting point, I believe, is to question the assumptions. These assumptions all were made when we had only electromechanical systems 50 or more years ago. And this is a quote I like: "It's never what we don't know that stops us. It's what we do know that just isn't so." And there are too many things that we know or think are true, and they used to be true. But they're no longer true, but we still believe them, and we're still taught them. So first of all, what is the traditional approach to safety? Traditionally, we viewed safety as a failure problem, as a reliability problem. And we assume that there is a chain of directly related failure events that leads to the loss. A fails, which causes B to fail, which causes C to fail, which leads to the explosion. And that assumption, that model, underlies and forms the basis for most safety engineering and reliability engineering analysis. For example, tools that you may be familiar with: fault tree analysis, FTA; PRA, probabilistic risk analysis; FMICA, failure modes and events analysis; event trees. It also forms the basis for the design approaches that we use. We either try to establish barriers between these chains of events. If A causes B causes C, then if we put a barrier between so A can't cause B, then we solve the problem. Or we try to prevent individual component failures. And we use techniques as redundancy, over-design, meaning design things to be stronger than we think they need to be, build in safety margins. We use interlocks. We use fail-safe design. All of these techniques and this approach is just inherent in everything that are part of everything the engineers do today. The problem is it doesn't work anymore, or at least it doesn't work as well anymore. Another way of thinking about this chain of events model is as a set of dominoes, where the first one falls, which then causes the second one to fall, which causes the third one to fall, and so on. So, for example, in the DC-10 accident in 1974, which still is, does this work? Oh. Well, sort of. All right, we'll have to go with that. Which happened a long time ago, but is still one of the most deadly accidents in aviation history. The cargo door failed, didn't shut closed as it should have, which caused a decompression, and the floor collapsed in the aircraft. All of the hydraulic lines, control lines, went through the floor, so all the hydraulics failed, which caused the airplane to crash. That's the standard way we think of each of these failure events. The problem is that it doesn't work anymore today. It's only a random failure, sir. It'll never happen again. This is not random failures anymore. We have systemic design errors in our systems and in our software. So the first point I want to make is that safety is not equal to reliability. Accidents happen with no component failures, and components may fail and not have any accidents. So this confusion is inherent in lots of things that we do. So we have a lot of techniques that identify the scenarios that involve failures. Some of those techniques do cause accidents, some of them don't. But there's a whole other set. That isn't a circle, is it? It's a circle here. What does that look like? Ah, interesting. It's supposed to be a circle. If we look over here on this circle, these are the unsafe scenarios. And you can see that some of those unsafe scenarios have nothing to do with reliability. It's those problems that we're not handling with our old techniques. Here's an example. This is an accident, a real accident, and it was in a chemical reactor. The computer controlled a valve here that allowed catalysts to come in and start the reaction. The computer also controlled another valve that allowed cooling water to go into the reflux condenser that cooled off the reaction. And the computer had only one other job. It's very simple, actually, relatively simple computer software. The software engineers were told if you get any input, there were some sensors in the plant. And the software engineers were told if you get input from these sensors, it means that something has gone wrong in the plant. And so what the software should do is to sound an alarm and call the operators and stop everything. And that's what happened one day. There was a low oil level in a gearbox. So the computer was told about the low oil level. It sounded an alarm, and it told the operators, and the operators went to the gearbox. The computer software worked exactly correctly. The problem was that the software opened this valve before it opened this valve. When it stopped everything, there was no cooling water. The operators went to the gearbox and put oil in the gearbox. The reactor overheated and vented noxious, poisonous things into the atmosphere for the people around to breathe. Now, if you look at this carefully, there were no failures. Everything worked. Each component worked the way it was supposed to work. The problem was in the interactions between the components, in the system engineering. And in this case, part of the problem was the requirements provided to the computer. Nobody told the software engineers that they should open this valve before they open this valve. If they had told them that, they probably would have done it. It's not a hard thing to implement in software. So they could have done it, but they didn't know. And that's where we're having problems today. So there are two types of accidents. Component failure accidents involve single or multiple component failures. They usually assume random failure. We know how to handle these accidents, and we have lots of ways of doing that. But now we're starting to see these component interaction accidents. In these accidents, they arise in the interactions among the components, not in individual component failures. They're related to the complexity and the coupling, tight coupling, that we're building into our systems and that we can build in because of the use of software. So they're not caused by software, but they're made worse by the introduction of computers and software. The problem really is system design errors, system engineering errors. So the relationship of complexity to safety is very important today. In complex systems, in the systems we are building in nearly every industry today, the behavior of the system cannot be thoroughly planned, understood, anticipated, and guarded against. We are building systems that are intellectually unmanageable. That means intellectually we are not able to understand all of the states and anticipate all the states that the system can get into. We can no longer exhaustively test our systems as soon as we put software in them. And so what it leads to is unknowns in our system behavior. We need tools to stretch the intellectual limits, the limits of our mind, and to deal with these new causes of accidents. In fact, I've looked at hundreds of accidents related to software that have occurred in the last 30 years. Virtually all were caused by flawed requirements, not by coding errors, not by implementation errors, but the requirements were wrong. There were either incomplete or wrong assumptions about the operation of the controlled system or the required operation of the computer, or there were unhandled control system states and environmental conditions. For example, we lost an F-18 when it got into an attitude that the engineers had assumed was not possible for the aircraft. It was possible, the software didn't handle it, and the aircraft crashed. That wasn't a coding error, that was a system engineering error. In the Mars Polar Lander, we lost that. That was the one that crashed into the surface of Mars when it was landing. And the software was responsible for turning off the descent engines, the engines that slowed the aircraft's descent to the surface of the planet. When it reached the surface, the software was supposed to turn them off. How did it know it reached the surface? Well, there were some very sensitive sensors on the landing legs of the spacecraft. And these sensors gave a signal when the spacecraft had landed. It turned out nobody, though, told the software engineers that when the spacecraft was coming toward the planet, to slow down, there was also a parachute that was deployed. When the parachute deployed, there was a jerk on the spacecraft, which caused the sensors to give out a signal. Now, the engineers probably didn't bother to tell the software engineers about this because the software wasn't supposed to be executing then. But the software engineers decided to be more efficient and start the software early in order to even the load on the processor. So the software was running, it thought the spacecraft had landed, and it turned off the descent engines. Again, each component worked the way that the engineers expected it to work. The problem was in the interactions between the components and ones that had been unanticipated. So merely trying to get the software correct or to make it reliable will not make it safer under these conditions. In all these cases I talked about, the software was 100% reliable. Software may be highly reliable and correct and still be unsafe for three reasons. One, it correctly implements the requirements, but the specified behavior is unsafe from a system perspective. The requirements don't specify some particular behavior that's required, that is, they're incomplete, or the software has unintended and unsafe behavior beyond what's specified in the requirements. This cartoon, it says, in case you can't read it and make it slower for the translators, "Hello, Emily. This is Gladys Murphy up the street. Fine, thanks. Say, could you go to your window and describe what's in my front yard?" If we're going to solve the problem of safety, we have to get outside our own individual disciplines and get a bigger view of the problem. We can't just stay within software engineering or within mechanical engineering or within each of our disciplines and solve this problem. We've invented a lot of new terminology recently. Embedded systems, now they're called cyber physical systems. And people think this is new. Software has always been part of a larger system. Even accounting software or business software is part of a larger business system. It's just that we never considered these things. We can't isolate software development from the world around it. So we've had lots of problems, but when we have put it into systems physical systems that are dangerous, then the problems become safety problems. The second issue has to do with operators. Do operators really cause most accidents? Most accidents are blamed on the operators, the pilots, the operators in the nuclear power plant, whatever. But do they really cause it? Well, the traditional view of operator errors, that operator error is the cause of most incidents and accidents. So what we need to do is something about the operator. Suspend them, fire them, retrain them, or to do something about operators in general. Marginalize them by putting in more automation, rigidify their work by creating more rules and procedures. And that's what we do now, and we just end up blaming all the operators. Fumbling for his recline button, Ted unwittingly instigates a disaster. The button says, wings stay on, wings fall off. We know that behavior is always influenced by the system in which it occurs, the design of the system. So in the new systems view of operator error is considered to be a symptom, not a cause. All behavior is affected by the context in which it occurs. We build systems where operator errors are inevitable, and then we blame the operator for the error. One of the examples, we were talking about security earlier. We build security systems and security techniques where we expect humans to have hundreds of passwords, all that which are random letters and numbers and characters, and they aren't allowed to write them down. And then we blame them when they write them down. Well, nobody can remember hundreds of passwords that are unmemorable. Or we build systems that system administrators can't install correctly, or some of them can't, and then we blame them when the accident occurs instead of looking at our system itself and the design of the system. The other thing that's happening is that the role of operators in our system is changing. They're no longer pushing buttons and reading gauges. They're supervising automation rather than directly controlling the system itself. A pilot in a new modern plane only flies the plane directly for a few minutes on any flight. Most of the time is spent, the automation is flying the plane, and the pilot is supervising the automation. But our systems are becoming so complex that the operators can't understand them. So we're designing, as I said, systems in which operator error is inevitable, and then we blame the accidents on the operators rather than the designers. In order to do something about operator error in this new systems view, we have to look at the system in which people work, the design of the equipment, the usefulness of the procedures we give them, the existence of goal conflicts and production pressures, pressures toward more productivity. Human error is a symptom of a system that needs to be redesigned. It is not a cause in itself. So what we've got is, in this cartoon, the birds are saying, it's still hungry, and I've been stuffing worms into it all day. We are trying to do the right thing, but we're using techniques for a different problem, a problem that used to exist and doesn't exist today. So what do we need to do? We need to expand our accident causation models. The chain of events model is no longer true in today's systems. It's too simple. We need to create new hazard analysis techniques. We need to use new system design techniques. Most of our techniques now work after we have a design. At that point, it's too late to make many changes. So engineers say, we can't change that. It's too late. Or if you have to change it, the cost of redoing the work is enormous and often prohibitive. We need to integrate safety analysis and cognitive engineering into our system engineering activities instead of making them separate and after the fact. We need to learn better from the events and the things, accidents that do occur. And I'll talk more about all of these. We need to improve the control of safety during operations. And we need to improve management decision-making and safety culture. And I wrote a book about all these topics, Engineering a Safer World, which has not been translated into Japanese, but I understand it's in the process, or they're somewhere in the process. It's in Chinese already. And it's based on, I'm going to talk about a few things in this book. It's based on this new accident causality model called STAMP, which stands for Systems-Theoretic Accident Model and Processes. It's based on systems theory, not reliability theory like the older techniques. It applies systems thinking to safety. So what does that mean? Well, accidents, instead of being thought of as simply chains of events, failure events, instead we envision them, we picture them as, treat them as a complex dynamic process. They arise in the interactions among humans, machines, and the environment. Basically, we treat safety as a dynamic control problem. Just like you learned in your control theory class, if you took a control theory class. Safety requires enforcing a set of constraints on system behavior. It's more than just preventing failures. It's constraints on the behavior of the system. I'll give you some examples in a second. Accidents occur when the interactions among the system components violate those constraints. So safety therefore becomes a control problem rather than just a reliability problem. Here are some examples of safety constraints. Power must never be on when the access door is open. 2 aircraft must not violate minimum separation requirements. Aircraft must maintain sufficient lift. The public health system must prevent exposure of the public to contaminated water and food products. So what we're doing, as I said, is treating losses as a complex dynamic process and safety as a dynamic control problem. What this means basically is that we're changing emphasis where too many things up here. Where our previous emphasis was on preventing failures, and now we're emphasizing enforcing safety constraints on system behavior that may involve preventing some failures. But it's more than that. And it's not all failures. It includes it, but is not equivalent to it. So here's some examples. In the Space Shuttle Challenger, the O-ring did fail. But the problem wasn't just that the O-ring failed. The O-ring didn't control the propellant gas release by sealing a gap in the field joint of the spacecraft. The goal was it didn't provide adequate control over the gas release. The software didn't adequately control the descent speed of the Mars polar lander. At Fukushima, there was not adequate control over the release of radioactivity from the plant. In Deepwater Horizon, the big accident we had, oil platform accident in the Gulf of Mexico not too long ago, there was not adequate control over the pressure in the well. The financial system didn't adequately control the use of financial instruments in our latest financial crisis. This applies more than just to engineering systems. So what do we do if we treat safety as a control problem? The first step is to identify the safety constraints. And then we design a control structure to enforce the constraints on system behavior and adaptation in terms of the physical design, the operations, management, and the social interactions and culture in the organization. This is what I mean by a safety control structure. I know this is small, but you don't need to see the details of it. It's the bigger picture that you need to see. Over here in red is the operating process. Here's the physical process, an automated controller, and maybe a human operator supervising this whole thing. Here is a control structure for operations. This is the control structure for development on the left. On the right, above the operating pressure, we have operations management. Above that, company management. Above that, government regulatory agencies, industry associations, the courts, insurance companies. Above that, the government. In development, we have the same thing at the top: government, then regulatory agencies, user associations, unions, then company management, project management, design and documentation, implementation assurance. Over here is manufacturing. There's interactions here in maintenance and evolution. Between each of these levels of the control structure, there's a control loop with company management, for example, setting safety policy standards and providing resources and getting back operations reports as feedback. This whole structure works together to ensure that systems are safe. We can't just look at this or look at this. We have to look at the entire thing. In Fukushima, I've been reading that there were problems in the interactions between the government agencies and the companies, and conflicts of interest. we have to look at that and control that in order to prevent accidents, serious accidents. We also can do this down within the physical system. This is an example for an adaptive cruise control in an automobile. BCM is the brake control module. We have an operator, controls instruments. The instruments send messages to the adaptive control module, cruise control module. That sends a signal, braking signal, to the brake control module, which gets a feedback back about the brake status, the vehicle's speed. The brake control module sends a braking signal, which leads to braking the vehicle. There's also the powertrain, which affects the electronic throttle, which affects the vehicle. There's other inputs. For example, radar shows the distance between two vehicles. Now I want to look more generally at this idea of a controller. Every control loop, there's a controller and a controlled process. The controller provides control actions and gets feedback about those control actions. Within the controller, there's an algorithm that's implemented and a process model. The process model is the model of the state of the controlled process. In software, this may be just a few variables. In a thermostat, for example, which doesn't seem to be working well in this room, you set a temperature, and that's the set point, and the thermostat provides control actions to maintain the temperature, and it gets feedback about what the current temperature is. Accidents often occur when the process model is incorrect. And in fact, that's most normal for software-related accidents and for operator-related accidents. In the Mars Polar Lander, the software thought that the spacecraft had landed. So the model of the state of the spacecraft was different, its model, than the real state of the spacecraft. And the model became unsynchronized, inconsistent, because of a feedback problem between the control process and this model. So the problems are that accidents occur when the process model becomes incorrect or inconsistent with the state of the actual system. And that's a much better model for why software contributes to accidents, or humans, than to talk about software failing. The software didn't fail, it did the wrong thing. And there are 4 types of unsafe control actions that the controller can provide. Control commands that are required for safety are not given. In air traffic control, 2 planes are on a collision course, but there's no command given to turn one or both of them away. Unsafe ones are given. 2 planes are not going to collide, but commands are given that make them collide. Potentially safe commands are given, but too early or too late, or control stops too soon or is applied too long. Now we can take these ideas and create a new way of analyzing safety in a system. Here's a more complete control loop. Here's the controller, here's the actuator, here's the controlled process, here's the sensor that provides the feedback. The process model, and what we can do is look at each part of this control loop and see how it can contribute to an accident. So, for example, I talked about the process model being inconsistent, incomplete, or incorrect. In addition, the actuator may not operate adequately. There may be delayed operation. The components may fail in the controlled process. We still do have component failure. And we still have to handle that. But if we just say in the controller, the software, it failed, that doesn't provide us with any information at all. There may be feedback delays, measurement inaccuracies, incorrect or no information provided. The sensor may not act out adequately, which may further delay the feedback, and so on. And what we're going to do in the new hazard analysis technique is to use this information to identify potential causes of an accident and to analyze the safety of particular systems. But let me just first summarize this. Basically, what I've been saying is that there is, at the bottom here, a new theoretical causality model I call STAMP. It's not a tool or anything else. It's a model of assumptions about how accidents occur. But on that basis, we can create many tools. For example, CAST is a tool to analyze the cause of accidents that have occurred. STPA is a hazard analysis technique I'll talk more about that takes a design or takes a system and identifies ways that an accident could occur in that system. There are specification tools because specifications are critical. We can do organizational and cultural risk analysis. We can identify leading indicators. And now we figured out how to apply this to security. So what I want to do is talk about a couple of these. One, STPA, a little bit about CAST, and a little bit about the security analysis. So what is STPA? It stands for System-Theoretic Process Analysis. The good news and the advantage of it is it can be integrated into system engineering, so it can be used from the very beginning of a project. It can be used to guide the design. It's so expensive. We all know the most expensive thing is redoing things after they've already been done. At the beginning, it costs almost nothing to make good decisions. It costs an enormous amount to undo bad decisions. So if we can build safety in from the beginning, it costs almost nothing to make our systems safer. We can use it for guidance and evaluation and test. Boeing has just adopted STAMP and STAMP tools in their evaluation and test of new aircraft. And it can be used for incident and accident analysis. It works also on the social and organizational aspects of the systems, not just the physical ones. It creates system and component safety requirements, the constraints. Remember I said virtually all accidents in software have come from bad requirements, inadequate requirements. We can use this analysis to generate the safety requirements, and I'm going to show you how. So we can make sure that the software safety requirements, for example, are correct, because we're going to generate them ourselves from this technique. And it identifies flaws in system design and scenarios leading to the violation of one of these requirements. There's a set of steps in STPA. We first identify the potential accidents and losses. Then we identify the hazards. We're going to do this on an example. Construct the functional control structure. Identify unsafe control actions. Generate system and component safety requirements. Identify the causal scenarios for the unsafe control actions, and then augment the system design and the safety requirements from this information. So what I want to do is do this for that example I showed you earlier, the batch reactor. Remember I said that the problem was nobody had told the safety engineers, or the software engineers, the software engineers, they hadn't been told that they should always open the water valve before they open the catalyst valve. So how do we get that information? Well, we start from a control structure. The hazard is easy. It's overheating of the reactor. So we're trying to prevent overheating of the reactor. Now, this is a physical structure. We usually make all our documentation in terms of physical structure. Even in software, we use physical structure. What we're going to do instead is create the functional control structure. So here's the functional control structure, the high level for this system. There's an operator that controls the computer that controls the valves. We have a process model. We have some instructions. Let's do this first. Instructions that go down. The operator can send a control command to start the process and to stop the process. The computer can send commands to open the water valve, to open the catalyst valve, to close the water valve, and to close the catalyst valve. Okay? Now, we also have feedback. We may not know what this feedback is yet, what we required, but we can figure that out as we're doing the analysis. There's feedback from the computer to the operator, which is about feedback about the alarm, whether there's an alarm or not, what the status information about the plant. There's also some information coming into the software, the computer, about status information on the plant. For example, in this case, it was the level of the oil in the gearbox was the problem. There's a process model in each of these. The process model in the computer says whether the water valve is open, closed, or unknown, whether the catalyst valve are open, closed, and unknown, whether the plant state is okay, not okay, or unknown. Now I'm going to skip about unknown. We're just going to leave that for the time being. The operator also has a process model. It needs to know the state of the plant, whether it's okay or not, and the state of the reactor, whether it's operating, not operating, or unknown. All right, so now the first thing we want to do is figure out what are the unsafe control actions that the computer can give out. We're going to just look at the computer for this case. And we do that. So the hazard we're looking at is that there's catalyst in the reactor without the reflux condenser operating, without water flowing through the reflux condenser. Okay? And you can build a table. This actually, the idea for doing a table came from JAXA people. And we build a table, and on the left-hand column here, we look at the various control actions that the computer can give. Open the water valve, close the water valve, open the catalyst valve, close the catalyst valve. Across the top in each column is one of those 4 types of unsafe control action. Not providing causes the hazard, providing causes the hazard, incorrect timing or order causes the hazard, or stopped too soon or applied too long for continuous operations. Now, what we do is fill in the table. So I'm going to start this off with opening the water valve. What we want to hear is the conditions under which not providing that command, in other words, not opening the water valve, could lead to that hazard. And we see that it's water valve not open when the catalyst is open. Okay? So what we have in here is the context under which not providing that command will cause an accident. Think about this. It's usually I have a small group, so I can ask you to do it. But think about it. Is there any situation under which providing the open water valve could cause the hazard? And I think the answer is no. So there wouldn't be anything in that square. You might waste water because you have more water going through when you don't need it, but it's not a hazard. It won't cause overheating. What about incorrect timing or order? What about if we open the water valve after we open the catalyst valve? That was actually what happened in the accident. Stopped too soon or applied too long, well, maybe the valve opening stops too soon. All right, so here's the answer to that line. What I want you to do is just take a piece of paper or do it in your head. Fill in that second line. What would you put in these boxes, or not put in them, for close the water valve? Are there conditions, for example, where not closing the water valve would cause the hazard? So think about the whole line. So here's the answer I got. Not closing the water valve, again, wastes water, but it doesn't cause overheating. Closing it while the catalyst is open could cause overheating. Closing the water valve before the catalyst valve closes could cause overheating. Stop too soon, doesn't matter. And we can do, you just learned how to do half of STPA. Not very hard. And we can fill in this whole table. So for example, open the catalyst valve. We open it when the water valve isn't open. Or down here, close the catalyst valve. We don't close it when the water has been closed. Some of this is a little redundant, but it doesn't matter. Redundancy doesn't hurt. It's missing things that hurts. So we can take this information and create our software requirements. So take that table, and we can generate the requirements. Water valve must always be fully open before the catalyst valve is open. And the catalyst valve must always be fully closed before the water valve is closed. Now, when I was first looking at this accident, my first guess at the requirements was the first one. I always have to open the water valve first. I have to admit, I missed that I also have to close the catalyst valve first. But we came up with it as soon as we went through this procedure of thinking through all these cases. That's step one of the process. We still have more to do. In step two, we need to identify the causes of these things happening. Here's our requirements. Why might those requirements not be satisfied? What could happen? And then we'll use that information to design to prevent these things. So step two, we want to identify some causes of the hazardous control action. Opening the catalyst valve when the water valve hasn't opened. So let me just give you a hint to start this process. Consider how the controller's process model, in other words, the software's process model, could identify that the water valve is open when it's not, and therefore not open it. It thinks it's already open. Again, I would normally let someone in the audience come up with these solutions. If we look at this thing, though, one thing that could happen is that the software gives the control action, tells the water valve to open, and what happens then? The software then thinks it's open because it issued the command to open. But what if something happened down here and it didn't open? Then the software could then open the catalyst valve because it thinks the water valve is open, but it hasn't opened. Right? So how do we solve that problem? Well, one thing is to provide feedback. So we provide some indication that the valve has actually opened. That might be a way of preventing that problem. So what we do is perhaps put in a flow monitor in the system to show that water is actually flowing through the system. There may be other solutions, other design techniques. All we're doing here is trying to help the analyst and the designer, the software and the system engineer, create a safe design. We also have to figure out some causes for a required control action, like open the water valve being given by the software but not executed. That may be, for example, some component failures. The solution, let's say the actuator actually fails, doesn't open it. The solution turns out to be the same, feedback. And so on. What else do I have? Oh, and I talked about design features, controls you might use to protect from the system from the scenarios you found, and that's sort of the next step. Once you found the scenario, then you design it out of the system the best you can. Okay, so that's a real quick lesson in STPA. It's not hard to learn. We have a primer that we provide with examples. It's been done on all kinds of systems by hundreds of people around the world are using this now in all kinds of industries. So there are lots of examples we have. Is it practical? It's being used, as I said, on spacecraft, aircraft, air traffic control, unmanned aerial vehicles. RPAs is the new term for unmanned air vehicle. It means remotely piloted aircraft. Defense systems, automobiles, GM, Ford, Nissan. I think we're starting a collaboration with Nissan. I don't know how much they've done yet. Medical devices and hospital safety, chemical plants, oil and gas, nuclear and electric power, CO2 capture, transport and storage, and so on. Just about every safety-critical industry now has someone using this on it. We also have used it on social and managerial systems. For example, analysis of the management structure of the space shuttle program after Columbia, risk management and the development of NASA's new manned space program, food safety, safety in pharmaceutical drug development, risk analysis of outpatient gastrointestinal surgery at a large hospital in Boston, analysis and prevention of corporate fraud, and so on. Does it work? I mean, you can use it. The question is, does it work? We know it's practical, at least. Well, most of these systems are very complex. For example, it was used on the new U.S. missile defense system, which is one of the most complex systems man has ever attempted to build. In all cases where a comparison was made in all of these systems, STPA found the same hazard causes as the old methods, as fault trees and HAZOP and all the other ones, FMEA. Plus, it found more causes than the traditional methods. It sometimes actually found accidents that had occurred that the analysts didn't know about, that the other methods missed. I'll mention that again later. What was surprising to me is the cost was orders of magnitude less than the traditional hazard analysis techniques. I thought originally that this would be more expensive because it's more powerful. It turns out it's easier and less expensive. That amazed me, and very much less expensive. Let me give you some examples. I said it was used on the safety assessment of the U.S. ballistic missile defense system. They called us in, they did this only right before the system was being deployed and field tested. We had 2 people for 3 months looking at this system. And they found so many paths, so many scenarios to inadvertent launch that deployment and testing was held up for 6 months while they fixed the problems. And it cost hundreds of millions of dollars to fix the problems. If they'd done it early, it would have cost nothing. They would have done it during the regular development. In many of the scenarios, just as we predicted, all the components were operating exactly as intended by the designers of those components, but the complexity of the interactions led to unanticipated system behavior. For example, turned out we found a missing case in the software requirements. There was a situation that if the operator happened to do something, at the same time certain information came in from the radars, it would inadvertently launch. It would launch a interceptor, and if that radar information was because of a 777 or something else, that would have been bad news. We found timing problems in sending and receiving messages. So there were cases where if you sent messages in a certain order, but they were received in a different order, and we found that you could do that because they were on different communication lines, so it could happen. There could have been delays. It could have led to an inadvertent launch. STPA also identified component failures that could cause inadequate control, but all the methods can do that. So this was a big success, one of our first attempts. JAXA has used this on the HTV, and I think Dr. Hoshina is going to talk about this after me. They found everything found in the fault tree analysis, but more, related to system design and software. We've tried it on new air traffic control procedures. The method being used by the US and Europe in these procedures were so bad it's hard to compare. But ours just blew them out of the water. We found many more scenarios than their use of fault trees and event trees. It's been done on nuclear power plants. There was an experimental comparison performed by EPRI, which is the Electric Power Research Institute. It's a research institute in the US that has members of the people running nuclear power plants. And they took experts on each technique and they gave them a design of a real nuclear power plant. STPA, again, found many more problems. But what was most interesting is that there had been an accident in that plant that they gave the design for, but they didn't tell the analysts about it. Only STPA found that scenario, accident scenario. And we looked back and we found that the other techniques couldn't have found it. It wasn't a component failure problem. This was, I'm just giving you a few examples. A blood gas analyzer, that's a medical device. Vincent Balkos is the person who built his company built the device, and he did this. The government, U.S. government, requires them to do a FMEA, failure modes and effects analysis. And the failure modes and effects analysis had found 75 scenarios, not the one that actually occurred. STPA was done on it. It found 175 scenarios to a patient injury by this device. It took much less time and resources, mostly human. The FMEA took a team of people a year to do. STPA took this one man 2 weeks. And yet it was much more successful. Only STPA found the scenario that had led to the recall. There had been an accident in this device and been recalled by the US government. Called a Class 1, which is the worst kind of recall. Actually, STPA found 9 scenarios to it, but only one of them we discovered had been the one that actually had occurred. There are lots more comparisons on the real systems. As I said, the biggest surprise to me was it required much less resources. Now, more good news. We've discovered how to automate a lot of the process. Whereas most of the other techniques have to be done by a human, we can automate some of this, especially step 1 so far we've been working on. I think we can automate parts of step 2, but that table that you saw. And so we can, John Thomas, one of my brilliant graduate students who's now finished, Dr. Thomas, we can take the hazards, generate the hazardous control actions automatically, and then generate model-based requirements. These model-based requirements are on a language called intent specifications spectrum, which is being used by JAXA, but it's very readable, but it's formal. And so we can do analysis on the requirements. So we can generate model-based specifications, requirements. We automate most of the step 1. It requires some human decision-making to step in. And I'll show you what that is. But the formal underlying discrete mathematical models allow for an automated consistency and completeness checks. We can detect conflicts. As I said, we've not yet automated step 2. Our language looks like this. I think I'm not going to go over it. But there is underneath it, it's very readable. It's a tabular thing people come in. We did this for TCAS, which is a collision avoidance system on aircraft that's actually used on aircraft. We did this for the FAA to certify it. And pilots and others could come in and learn to read this language in about 10 minutes with no mathematical background. Underneath there is a mathematical representation, but the users don't have to know about it. But it allows us to do analysis on these. So how do we basically do this? Well, think about what a hazardous control action is. For example, let's say we're looking at a train, and the operator provides an open train door command when the train is moving. All right, that's obviously hazardous action by the operator. It could be a computer provides. It doesn't matter whether it's a human or a computer. So there's a source, the controller. There's a type provides. There's the control action, open train door command. And then there's the context, when train is moving, which is actually the information that's in that table. We can write this in a formal, generate a formal notation, and human doesn't have to do this, done by a computer. And generate a table. Now this is a really part of a big table that was done for a real nuclear power plant. We did this for the Nuclear Regulatory Commission. We did a STPA analysis on a real nuclear power plant that's being built right now in the United States. And you don't have to know all this. The computer generated this big table. And what the human has to do is just come in and look at each of these and say, is this hazardous or not? Because we don't have a model of how a whole nuclear power plant works. But it's much easier than would normally be done. But we were concerned when we did this because there were 150 rows in this table. We had a nuclear engineer working with us, and he went through all this to find the hazardous control actions, to identify them. And we were apologetic. We said, it took him 2 days. And we said, well, this is just too big. And he said, oh, no. He said, it takes a team of people a year to get that same information using the techniques we use now. 2 days, one person is nothing. And we said, well, it's still too much. So we created a way figured out a way to prune this down automatically by having the engineer design rules for reducing this table. All right, so as I said, we can generate automatically, take these control actions, and then generate these requirements. And it's all because there's a discrete mathematical representation, a state machine structure underneath. Unless you're into formal methods, this doesn't really matter. Okay, that's STPA. The other thing, one of the other tools is CAST, which is a way of analyzing the causes of accidents. And we don't focus on blame. We try and focus. We don't look for something or someone to blame. We look at why the accident occurred. We identify the hazard violated and the design constraints that weren't satisfied, construct the safety control structure as it was designed to work, and then for each component, see whether it fulfilled its responsibilities or whether it provided inadequate control. If it didn't provide adequate control, was it because of context or because of process model flaws? For humans, you need to look at, we could just say, well, the human made a mistake. That's it. Go retrain the human. In the Air France tragedy, catastrophe, where that was the plane flying from South America to Paris, and it went into a stall and crashed into the ocean, and everyone was lost. What they said was, the pilots did the wrong thing, so therefore we should retrain the pilots. That's not enough. If you look at this, and we've done some analysis of this, and we've led some other people in aviation to do it, it turned out there were very good reasons for the pilot to make the mistake they made. And it was related to the design of the software and design of the avionics in the plane. If you just say retrain the pilot not to pull up in a stall, that's not going to solve our problem if the problem is in the design of the avionics. And so we need to do a better job. And then we look at other things. I'm not going to go into these details, I think. Let me just give you an example. This was an airplane crash that occurred in September 2006. It was a Comair plane. It took off from the wrong runway at Lexington Airport. That runway was a short runway. The NTSB, National Transportation Safety Board, did a report, very extensive report, as they always did, and basically said it was pilot error. We looked more carefully, actually. We didn't do it. A man, Paul Nelson, who is a Comair pilot for that airline, he also happens to be a human factors expert. And there's a report, if you're interested in seeing it, it's up on the website there. You've got the notes. Let me just give you a little example of what some of the other factors that were missed by the FAA. Here's the control structure. There's the flight crew. This is the airline, Comair management. This is the air traffic control facility at the airport. This is the airport authority. This is the FAA. This is Jeppesen, who makes airport maps. Now, why are they in there? Well, it turned out there was construction on the runway. That's why the pilots got confused. And the maps that they got were incorrect. As it turns out, by the way, everything in here contributed to that accident, not just the pilots. So if we only look at the pilots and stop there, we don't fix all the other problems. So let me just give you one of them related to software. The maps, charts are given to the flight crew, and they get updates every day if there's construction or changes. They never got an update telling them about the construction and the changes on the airport runway. Why didn't they get it? Well, that information was supposed to go from the FAA to this Jeppesen company that produces those notices. The information was sent at night. The Jeppesen computer was turned off at that time, so it never got the information about the closed runway, and therefore never got it to the flight crew. Now, things like that, factors like that, can help because we can fix those problems, right? Maybe, there are lots of ways to fix it. One is to require feedback to say, I received it. And if you don't get feedback, send later. Another is to make sure you collect information that comes at night. You may turn off your computers and generating maps, but don't just ignore any information that comes in, and so on. So all of these things together need to be fixed in order to prevent future accidents. And that's what CAST does. It helps to find all the factors. Again, Doesn't work on real accidents. It's been used on many types of accidents: aviation, trains, chemical plants, road tunnels, medical devices. All the analyses so far have identified important causal factors that were omitted from the official accident reports. In one example, for example, there was a man, John Hickey, who was a graduate student at MIT, who worked for the Coast Guard. And the Coast Guard had been having a lot of accidents within a certain period of time in training for helicopter aviation training, but they couldn't find. They used the standard technique, which is called HFACS, based on the Swiss cheese model, which is just the chain of events model, and they couldn't find any common factors. He tried cast on it, found common systemic factors that hadn't been identified that they could fix to prevent these accidents from happening again. The Dutch Safety Agency uses this on a large variety of accidents. We can also look at organizational aspects of risk. You can identify unsafe control actions and causal scenarios at higher levels. Most of what I talked about has been the physical level, and building controls. We can look at non-safety risks, including project risks, budget risks, schedule risks, the trade-offs between all of these. The goal may be to evaluate an existing control structure or to create a new one, or we maybe wanted to create leading indicators of risk, try to predict accidents before they happen. It's been used again on NASA safety management, radiation therapy at a Yard University hospital, CO2 capture, transport, and storage in France, and on the product development process itself. All right, one more topic and then I'm through. There is what we've discovered recently in the last few months is that we can handle security this way too. So I want to very briefly tell you, how do we handle security and safety doing the exact same things? Well, let's think about what is safety. Safety is preventing losses due to unintentional actions by benevolent actors, by people trying to do the right thing. Security tries to prevent losses due to intentional actions by bad actors, malevolent actors, evil people. The key difference is intent, but the common goal is preventing losses. We need to ensure that the critical functions and services provided by the networks and services are maintained, not just prevent attacks and incursions. Our bigger goal is to maintain the services or maintain the restrict access to information that we want to we don't want people to get. So an integrated approach is possible, and this new paradigm for safety works for security too. It's another top-down approach. Most of security, and I find the security world very frustrating. I didn't want to get into it because it seems like, somebody attacks something and Microsoft then fixes that hole, and then the next day they find another hole, or they find a flaw and they fix, and then they attack again, and we don't get anywhere, really. We're just fighting sort of a losing battle here. This is a top-down system engineering approach instead to security. It starts with identifying the losses that we're trying to prevent, identify the vulnerabilities and the system safety and security constraints, because we can think about security as constraints too, build that same functional control model. We're controlling constraints, whether those constraints are safety constraints or security constraints. It includes the physical, social, logical, and information operations and management aspects of systems. Too much of our security work never looks at management and social systems, and it just focuses on the low-level technical. And then we identify the unsafe or unsecure control actions and the causes for them using STPA. We may have to add in some new causes, but the rest of the process is the same. So let me give you an example, a quick example. Stuxnet. Stuxnet was the break-in, was the security intrusion in Iran, the Iran nuclear reactor. Remember, we put malware, well, we don't know who did it. Most likely it was the Israelis or the Americans or them together, because not many other people had the technical expertise to do it or the desire to do it. But somebody got malware on their nuclear reactor processing facility and kept the malware kept destroying and damaging the reactor. And they didn't understand why. They just kept replacing things. So the loss here is damage to the reactor. In this case, they were damaging the centrifuges in the reactor. The constraint, the security constraint, is that the centrifuges must never spin above the maximum speed. What happened was the malware made the centrifuges spin too fast and wore them out. So they kept having to replace centrifuges. So we were slowing down their ability to process nuclear material, fissionable material, to make a nuclear weapon. So the constraint then is it must never spin above the maximum speed. The hazardous control action is issuing an increased speed command when it's already spinning at the maximum speed. What are some causes? And our analysis would look at what are the causes of this. One cause is, again, an incorrect process model. It thinks it's spinning at less than the maximum speed, so it issues an increased speed command, which is probably what happened. That could be inadvertent. It could be accidental, just bad programming, bad development, or it could be advertent. It could be, as in this case, malware or an enemy doing this. It really doesn't matter. What we want to do is build this thing to ensure that it cannot spin too fast. And there's more about this written up, and this is very brief. Again, we're trying to evaluate this. Because this is so new, we've only thought about it in the last 6 months. We call it STPA security, SEC. Our evaluation so far has been informal, but it's because the student doing this with me is an Air Force colonel. He could get access to real red teams. So we've been doing this and teaching this to real red teams and comparing it with the standard techniques they use, which are something called attack trees, which are just fault trees. And they found things that they hadn't found before. We've now done more, I just found out about yesterday, on a real weapon system. And again, we found things that nobody had found before. Potential security violations and ways it could be attacked. There's going to be a formal experiment in the spring for his dissertation, and we will have more information. Just a couple more very quickly. I've talked about mostly safety and development. We also have to consider safety in operations. And operational safety starts from using the information in engineering development, passing it to operations and doing these things and passing feedback back. And there's a lot of steps we have to go through in operations. I'm not going to go through them. There's not time. There's a chapter in the book on it. We also have to think about management. So I have on safety culture. I have a chapter on why managers should care about safety, how to achieve project and company safety goals, and how to design an effective safety control structure. And that's all in the book, and just don't have time to go over that. So summary. What we found is that this is a more comprehensive and powerful approach to safety and security. It examines the interrelationships rather than just linear cause-effect chains. It includes what we consider now, which is component failures, but more than that, system design errors, requirements, flaws, and so on. It includes social, human, and software-related factors that the old techniques don't. It's a top-down system engineering approach, so we can use safety-guided design starting early at the concept formation stage. We're still working on this. We'll have a dissertation on this soon. JAXA has been trying this on their manned space program, spacecraft, the new one. And so they've been trying it too. We generate the safety requirements from the hazard analysis. And it handles much more complex systems than the traditional safety analysis approaches. That's what's very exciting, is that it handles these complex systems. You couldn't have even done a fault tree or a standard analysis FMEA on the U.S. missile defense system. I mean, it's just impossible. We would have spent 20 years doing it. This we could do in a couple months and find important problems. So what this basically does is, by using systems thinking, by looking only at event-based systems thinking, failure thinking, reliability thinking, we only see a small part of the iceberg. By adding systems thinking, we can get a much bigger picture of the problems. So I just wanted to tell you, I started having a workshop on this right after my book came out 2 years ago. And the first workshop, I expected 50 people, and 250 people came from 19 countries around the world. I didn't even know many people knew about this at that time. And we've been having workshops since, each time with people globally in every industry. This year, it's going to be March 25th to 29th at MIT. There'll be tutorials on STPA and on CAST. So we're going to teach people how to use it. There'll be presentation by current users about STPA CAST experiences they're having. There'll be a track on security, cyber security, how to apply it to security. There'll be research presentation, and people are building tools now. It was a little premature to build tools until we knew it worked and knew how to do it. Now we think we know how to do it, and people around the world are building tools. We're building some. There are some being done by the Volpe Center, which is a transportation research center in the U.S., and there are some being built by the University of Stuttgart, and they'll all be shown. And if you want information about that, it's there. All the past workshops are there, too, the presentations, and information about the one this year.